I'm going to begin with a simple science experiment that almost everybody in this room has probably performed at some point in their life, probably when they were much younger. I'm going to take a convenient object, in this case a piece of paper, and I'm going to remove half of it. And I'm then going to recursively continue the experiment. I'm going to remove half of what remains and remove half of what remains, and so on and so forth, until it becomes boring or until it becomes, the pieces get too small for me to manipulate. In the case of paper, it doesn't take very long for it to get boring because the physical properties of half of a sheet of paper are identical to those of a full sheet of paper, except for their dimensions. In the case of other objects, it's different. So if I had a zebra with me and I removed half of the zebra, we would quickly learn more than we might want to know about how zebras are put together. In the case of paper, because we live in a scientifically advanced society, we don't need to do the experiment for very long because we know already what we would discover if we kept tearing it up. Before long, I would be working not with sheets of paper, but with little lumps of plant fibers that had been matted together in the paper-making process. And if I kept tearing those up, we would learn that they were made of strands of cellulose, which is a naturally occurring polymer. And if I could tear the pieces of cellulose up, we'd end up with monomers, which are little molecules, and those could be subdivided into atoms and subatomic particles, and so on. All such experiments tend to be some mix of physical science experiments and a more metaphysical kind of discourse. And I've just given you examples of both. So as long as I'm tearing up sheets of paper that you can see, I'm doing a very simple kind of science in that you can look at the paper, you can come up here if you wanted and verify my observations or refute them. When we move on to what I'm calling the more metaphysical style of discourse, there's a fundamental change that takes place because now instead of working with physical objects, I'm manipulating a mental concept that's in my mind and apparently in your mind of what a piece of paper is and how it's put together. And instead of physically tearing it up, I'm describing kind of hypothetical experiments, thought experiments or Gedanken experiments that we could carry out on such a piece of paper, and we're making sort of reasonable guesses as to what would happen if we did that to the model of the paper that's in our head. At that point, the verifiability or lack thereof of the experiment becomes a different sort of thing. It depends upon the degree to which my mental model of a piece of paper jibes with yours. And it depends upon how convincing I can be in explaining what I think will happen when I tear it in half. This sort of procedure sounds a little bit dodgy when I explain it in those terms, and indeed it can go spectacularly wrong, but it is a legitimate way of doing science. The scientists of the 20th century, the physicists like Einstein, and for all I know, physicists today, use these Gedanken experiments in order to search for holes in existing theories and even to guess what properties new theories might have to have in order to avoid those same pitfalls. The Greeks were very comfortable with this way of thinking with very mixed results. So in the case of geometry, for example, when I was a boy, I was taught that a line or a line segment was an infinite number of geometric points arranged in a particular configuration. And I was also taught how to bisect a line segment using nothing but a ruler and a compass. So I had everything I needed in order to carry out the paper tearing experiment on line segments. But that experiment rapidly becomes even more boring than tearing up the paper, because with the paper, at least, we eventually get to something different. We get to cellulose or molecules or atoms. But when you bisect line segments, you always end up with just another line segment. You can make a sort of metaphysical leap and postulate that if you could do it an infinite number of times, you would end up with a zero-length object called a point, which is different. It is qualitatively different from a line segment, You can predicate things of it that you can't predicate of lines, and vice versa, which might seem to be sort of a mincing, hypothetical kind of distinction, but apparently it was enough that the ancient Greeks were able to build on that, this edifice of Euclidean geometry, which is really a quite remarkable system of interlocking proofs that is all sort of consistent and self-reinforcing, and that is used every day for practical calculations. So that's a case in which this approach worked pretty well. In the case of material substances, it didn't work so well. So they sort of mentally did the experiment of subdividing a physical object. And when you play that game, there's really only two ways you can go. You can either say that it's turtles all the way down, as the expression has it, meaning that you can go on subdividing forever, or you can place a floor underneath the subdivision and say that at some point it can happen no longer, and you are working with objects that are, by definition, atoms. They cannot be further subdividable. So the Greeks did that, and to that point it was fine, but then they began trying to make statements about the properties and the shapes of those atoms, and everything from that point on was rubbish. So they were able to, their atomic theory was able to tell us things about their elements that we already knew, such as fire hurts and water is slippery, but it couldn't create any new verifiable predictions. So it didn't really enter science except as a kind of curiosity from the history of science. So this kind of thinking was prevalent around the time that I'm going to be focusing on, which is this sort of heyday of the Royal Society, the scientific revolution, the careers of Newton and Hooke and Leibniz. Leibniz referred to this general sort of inquiry that I've been describing as the problem of the composition of the continuum. And he said that it was one of two great intellectual labyrinths into which the human mind tended to be drawn. The other one, in case you're curious, was the problem of free will. Anyway, during this era, you've got, for example, Robert Hooke looking at things through his microscope. And he's noticing, for example, that when you look at man-made objects, the results are pretty boring. You just sort of see the same thing except nastier. Whereas if you look at living objects, it just gets more and more interesting the more you look. And if you look deep enough, you find the thing that Hooke calls a cell. So you look at a zebra under a microscope, you don't just see a lot of tiny zebras. You see these things that clearly are not zebras, but if you understood presumably how they worked and how they interacted with each other, you'd be able to account for all the properties of a zebra. Hooke and Christian Huygens and others are working on building the first proper clocks. And that is fostering a way of thinking about time as a physical quantity that can be measured precisely with an instrument, the way we measure distance with a ruler. And if you can measure it that way, you can subdivide it and play this sort of atomistic game with it, and perhaps arrive at a fundamental unit of duration that is to a span of time what a point is to a line or an atom is to a substance. And Leibniz and Newton are at about the same time inventing or discovering, take your pick, the calculus, which, without going into a lot of detail, is kind of what you get if you apply this sort of atomistic approach to the study of continuous mathematical quantities. You sort of take something that is too complicated to work with, and you keep breaking it down until you get something that's different, and then you do something clever with the tiny little thing and reintegrate it to make the big thing again. And suddenly you're able to calculate the area under a curve or something, which you were not able to accomplish before. So in the midst of all this, Leibniz makes a very interesting philosophical move, which is, he says, I'll give you that space and time are some fundamental constituents of reality, and I'll give you that by subdividing them into tiny little bits, that we can do science and learn new things about the universe. I'm even inventing some of the math that's used to make that program a reality. But I put it to you, says Leibniz, that there is a third fundamental constituent of reality that should be treated with the same level of dignity in the sense of rank and priority as space and time, and that is cogitation. It's what minds do, it's what souls do, it's what God does. And he's not having any sort of program in which the activity of minds is going to be treated somehow as a sort of epiphenomenon, a result of the operations of spatio-temporal things. Later on, he strengthens that position and he states that cogitation is actually prior to and has a sort of more fundamental level of reality than space and time, that basically space and time are epiphenomena of cogitations. And he says that we can play the atomistic game with thoughts, with ideas, and that if we subdivide cogitation into the tiniest possible little bits, we end up with the sort of atoms of thought, the atoms of cogitation, which he calls monads. And he says that if we understand what monads, how they operate, how they interact, then we'll be able to achieve great things and to understand how greater thoughts and greater ideas are formed, and we'll even be able to form new thoughts and new ideas. So, and he says that he's creating a science of this that's called monadology. And so I guess it sort of behooves me to talk about monadology now. And that's turns out to be quite difficult and frightening. So instead I'm going to go on a digression. It's a digression about a digression. It has to do with a friend and an older colleague of Leibniz by the name of John Wilkins, who more than any other one person was responsible, in my opinion, for the creation of the Royal Society as a viable entity. He was not a great scientist, as I'm about to demonstrate, but he did have what we would today call the emotional intelligence, the social skills, and the sort of political savvy needed to make the society work and indeed to make it royal. Wilkins wrote a book called An Essay Towards a Real Character and a Philosophical Language, which was his attempt to create a new language, a synthetic language like Esperanto, that was going to become the language of science. They called it natural philosophy back then, but I'm going to use the term science. It was going to be the language of science. It was going to replace Latin, which is, of course, a natural language. And the reason that Wilkins's language was going to be better at that is that, among other things, for everything that could conceivably be the subject matter of a sentence, there was going to be one word and one word only in this language. And so in order for him to create this language and write this book, he therefore had to draw up a list of everything. Every animal, every plant, every abstract concept, every manufactured object, every disease. And he had to put it all into his book, which he did. It's organized in what we would today recognize as outline form. So there are top-level headings like plants and animals, and then subheadings and sub-subheadings and so on. And of course, as we all know, if you've got something organized in that hierarchical structure, you can identify one entry pretty efficiently by listing a string of numbers. So you can say it's in top-level heading 1, subheading 3, sub-subheading 4, sub-subheading 6. Then the number 1, 3, 4, 6 is sufficient to identify uniquely that entry. His alphabet was simply a way of enciphering numbers. And so you could look at a word, an unfamiliar word that you had maybe never seen before and didn't know how to read. You'd be able to parse it as a string of digits and then go into his tables and identify exactly what that word denoted. Likewise with the system of pronunciation. So there's a moment in this book where, I'm putting on my novelist hat for a second, where I imagine Wilkins sitting up in the middle of the night, drenched in sweat, with terrible nightmare visions of being burned at the stake. And that's what causes him to go on this digression. And the problem that he's created for himself is as follows. In the Bible, Noah's Ark is described very specifically as having certain dimensions which are expressed in cubits. And the numbers are called out in the Bible. Those are not changing. The problem is that Wilkins had just, because he was maybe the best connected scientist of his era, he had just succeeded in drawing up what was certainly the longest list of animal species that had ever been compiled since the time that the Bible was written. This is an era when people were scientists were being actively persecuted by the church. At the moment when he's writing, England is Protestant, but very powerful people are working quite strenuously to flip it back into the Catholic camp, and it's quite likely that he may end up being under the authority of the Inquisition at some point. And even if that were not the case, Wilkins was the Bishop of Chester. So he had his own position and job security to think about. So he stops, he brings his book to a screeching halt in the middle, after the animal list, and he says that he's concerned that a certain category of readers of this book, whom he describes as atheistical scoffers, may use his list of animals as a way of proving that the Bible is wrong. And so he's going to go on a short digression and demonstrate that this is not the case. He then goes into a little disquisition about how long a cubit is. Of course, it's supposed to be this distance. He refers to a number of authors who have apparently been worried about the same problem, who've been trying to come up with longer definitions of the cubit. The sacred cubit, they called it. The one in the Bible was perhaps longer than the length of your forearm. And here Wilkins begins to show some talents as a kind of intellectual prestidigitator. You may have seen a magician about to perform a magic trick that might be explainable by an object hidden up the sleeve. He'll very carefully roll his sleeves up, push them up to the elbows in order to show that this isn't the case. Wilkins makes the same move now. After listing all of the ways in which he could get away with using a bigger cubit, he announces that he doesn't think that's necessary. He doesn't see any need to play around with definitions. He's just going to use the good old-fashioned cubit. And he goes on in that vein. He points out that merely having one breeding pair of sheep on the ark is not enough, because the wolves and the lions and the tigers have got to eat something. They have to eat fresh meat during the journey, which is quite long. And not only that, but he wants them well fed. He's not going to skimp and feed them starvation rations. So a lot more sheep are going to be needed on the ark. And with a lot of drama and detail, he calculates the number of sheep required on the ark at 1,825. He then points out that the sheep are going to have to be kept alive long enough to be eaten by feeding them fodder. And he goes off on more learned discourse about the rate at which hay compacts when it's stored in haystacks, and the increase in hay density over time. And he performs this big calculation and announces at the end, in a great sort of ta-da moment, that the ark as described in the Bible is perfectly adequate to carry everything needed. And then in a really audacious kind of flourish that I sort of admire, he says that the mere fact of his calculation doesn't just not contradict the Bible, but actually tends to demonstrate the veracity of the Bible. Because if the Bible were just a bunch of lies made up by some people trying to deceive a bunch of illiterate Bronze Age people, they would have used different numbers. They didn't have his giant long list of animals. They didn't have access to the latest data on hay compaction rates. There's no way that they could have come up with those numbers in their state of ignorance. There's only one explanation, which is that it's all true. So, and then he goes on with the rest of the book as though nothing had happened. So a couple of things about this. One is sort of the relationship of these people to religion at the time. It's impossible to know what sort of expression was on Wilkins's face when he was writing all of this. It is a little bit reminiscent of a bit in Gibbon, where Gibbon is talking about all of the miracles in the early church, and he stops for a while to say, isn't it strange that during that time they had miracles left, right, and center, but we never have miracles now. So when did God stop with the miracles? You know, was it a certain fixed cutoff date? Was it later in the medieval period? To the atheistical scoffer type of reader, it seems it's funny. It seems like he's writing it all with a little bit of a wink and a nudge, but it's all phrased in a way that if he were called on the carpet by furious churchmen, he would have what we now call plausible deniability. So was Wilkins one of those guys? Was he taking that approach here? I tend to think not. My take on it is that nowadays we tend to sort of divide everyone into the Richard Dawkinses and the Sarah Palins of the world, but that, and everyone's either one or the other. But then as now, I think there's room for a lot more ambiguity and shading in one's positions. And that is applicable to Leibniz, who, as we'll see in a minute, was kind of in a similar boat for a while. The other thing I'll say about Wilkins is that although I've been sort of playing the story for laughs, what he was doing was actually part of a larger program that Wilkins and Leibniz and some of their pen pals worked on throughout their whole careers. And it was to build what Leibniz described as the characteristica universalis, which was kind of a hard thing to explain, but we can sort of get a sense of it from the way Leibniz described it to other people. So he said that it was going to be a machine, a device that would increase the power of our cognitive faculties in the same way that telescopes have increased the power of human vision. And he said to someone else that this system, if you ever got it up and running, would perform calculations on things that were not mathematical in nature. Of course, today we would say that if you can perform a calculation on it, it must be mathematical in nature. But I think what he meant was that it was going to be a machine for creating new knowledge and new wisdom by carrying out kind of symbolic logic operations on ideas, on sentences. And part of that is certainly Wilkins's language. You need to have that if you're going to build the characteristica universalis. Leibniz actually criticized Wilkins's language, saying that it was too practical, which is a real howler if you've ever actually seen Wilkins's language. But what he meant by that was that it was really just a list of terms, and it didn't have any of what we would today call the executables. But we know that Leibniz was one of the first people to work in the field of symbolic logic. We know that for a while he was the world's foremost inventor of calculating devices. He built, or caused to be built, a machine that could perform multiplication and division as well as addition and subtraction. And we even know that he was one of the first people, if not the first, to experiment with binary arithmetic. So although I've sort of played the Wilkins story for laughs, he was trying to make a serious contribution to this program, and the only thing wrong with that program was that it came 300 years too early, but they didn't know that yet. So I've been avoiding the moment where I have to talk about monadology. Leibniz never writes it down in the same kind of polished, finished ex cathedra style that Newton writes down the Principia. It keeps changing throughout his life, and so the only way to figure out what he was thinking is to read the letters that he wrote to his various correspondents in various languages. And these change over time because his theory is changing over time, which is fine. And it appears that he may not be above dumbing down the description of it depending on his estimation of the intellectual capacity of whoever's going to receive the letter. So that makes it all pretty complicated to figure out exactly what these monads were and how they would work. We are modern computer using people, and even if we've never written a computer program in our life, we have a pretty good idea of how computers work, what their capabilities are. They are tools we use every day. And so if you're that kind of person and you're looking at monadology, you're a little bit like a mechanic looking at a really cool new machine that you want to figure out how it works, and you're holding a wrench in one hand and you're sort of looking around for anything hexagonal you can put the wrench on. But there are no hexagons on the monadology. There's no way in, no point of entry for a modern computer-minded person. So I rely on the work of a scholar by the name of Christia Mercer, who's at Columbia, who produced this book, Leibniz's Metaphysics, Its Origins and Development. And she actually does have what it takes to read through these letters and sort of sort it all out and figure out what Leibniz had in mind with the monads. And I'm afraid it's not terribly good news for those of us who just want to instantiate a huge number of monads and put them on the cloud and let them run and see what happens. So to begin with, Leibniz starts by saying that monads do not have a cause and effect relationship with one another. So that's a bit of a poser. I think what he's saying is that part of his agenda here is to carve out a kind of safe space for free will. He's trying to protect the precincts of free will from the encroachment of science, and he's gotten at least some people to agree to the proposition that cognitive activity is prior to spatiotemporal things. And how stupid would it be if his first move then was to posit some mechanistic cause and effect relationships among the monads. So he says that they, in effect, have a kind of independence and free will. Naturally, we'll want to know, if we're going to program monads into our computer, how they interact with each other. And Leibniz says that every monad knows the state of every other monad in the universe. So that too is a bit troublesome. It would be a lot easier if he said that each monad knows its neighbor's states, or the states of all the other monads within a certain distance. But he likens each monad to a mirrored sphere, a mirrored ball, that has on its surface a reflection of every other monad in the whole universe. So those are kind of his ground rules for how monads work. Professor Mercer says that internal and intrinsic to each monad is a rule, which she dubs the production rule, that governs how it changes its state in response to its current state and the perceived state of all the other monads. And just as the constraints of space and time are inapplicable to monads, so cause and effect work differently, for each monad is causally independent of all other monads. It makes its own decisions by its own lights, obeying its intrinsic rule. So that leads to the question of, do they really have independent action if they're just following a rule in response to the other monad states? Apparently, the way he gets around that is by saying that that these rules are an internal thing, and each one is following its own rule in its own way. It seems a little slippery to me, but no one said this was easy. The development of monadology after that is that after Leibniz's death, one of his disciples writes it down with some mistakes. And people reading that book actually tend to blame the mistakes on Leibniz. And then Kant blows it out of the water about 300 pages into Critique of Pure Reason. He just aims the big gun at monadology and kind of destroys it. And after that, in the rest of the 19th and early 20th centuries, the general trend is towards a less metaphysical style of thinking about these topics. And so people tend not to respect the type of work that monadology exemplifies. The rehabilitation of monadology begins around 1900 when Bertrand Russell speaks highly of it in Principia Mathematica. It's a bit of a surprise. He begins by saying some quite negative things about Leibniz the man, and then turns around and says, on the other hand, his monadology is quite nice, and I really like it. The other person who comes along later in the 20th century and spends a huge amount of his career on this is Kurt Gödel, the Austrian logician, the greatest logician since Aristotle, who in the second half of his life, when he's in Princeton, develops a fixation on Leibniz and on the monadology and on the Characteristica Universalis, and devotes sort of an infamous amount of time and effort to pursuing his studies of the same. So I'm just going to list a few. I'll begin by kind of stating what is probably obvious already, which is that monadology didn't lead to anything in the same way that, say, Newton's Principia led to a science based on verifiable predictions. So it's not, it doesn't fall into the same category. It's not real science, but it did have a lot of influence, which is still being felt. And so I thought I would list a few of the ways in which it became influential later. One is in this the free will thing. So the people are still getting lost in that labyrinth that Leibniz mentioned of considering the problem of free will. And it can be a difficult thing to reconcile with a worldview based on Laplacian determinism, where everything results from the operations of spatio-temporal objects that follow predictable laws. So Leibniz made an interesting move by to cut that Gordian knot by making free minds or souls into the fundamental components of the universe. The whole scheme of the production rule that I quoted from Mercer will probably remind some people of cellular automata. And the field of, in general, we say that cellular automata is a branch of math that was invented by Stanislav Ulam and John von Neumann during the 1940s as an outgrowth of work at Los Alamos. The abilities of those systems are quite impressive and have been come in for a lot of study in the last few decades. Although Leibniz's monads didn't lead in a traceable way from one to the other, the one was quite obviously a sort of precursor of the other. The thing about cellular automata is that they have very simple rule sets that produce shockingly complicated results. That becomes obvious if you've actually got a high-speed computer that can make them run for a while, and you can see the results. If you don't have a high-speed computer, it's very difficult to see in advance that a few simple rules can lead to such complex outputs. And Leibniz, of course, didn't have any of that. Leibniz's insistence that each monad perceives the state of all the other monads seems completely impossible on a kind of standard classical reading of information flow and how things work. How could that possibly ever be the case? While it is somewhat crazy, I will point out that there is a related idea in quantum physics. The Pauli exclusion principle states that no two particles, no two fermions can occupy the same physical state. That's what prevents atoms from collapsing. If it's true that no electron can occupy a state currently occupied by any other electron in the universe, then it sort of leads to the question of how does the electron know what all the other electron states are? If we try to think of that in terms of actual transmission of information and the storage of data inside an electron, it clearly becomes ridiculous. And yet, there does seem to be some sense in which individual particles can be responsive to the states of particles that are far away and not connected in any direct cause and effect sense. Again, I'm not claiming that Leibniz anticipated any of that. He certainly didn't, but it's kind of interesting. Leibniz said that the explanation for this coherent behavior of large groups of monads was a thing that he called pre-established harmony, which is a phrase that just asks to be made fun of. It has a sort of saccharine-sounding greeting card connotation to it, but it was actually kind of a serious idea. And again, without going into a huge amount of detail, you can see some continuations of it in the statistical or the group behavior of ensembles of particles. The ideas like the Hamiltonian and the Lagrangian of the system of classical particles treat the system as an ensemble or as a group rather than as individual objects. And although all of those objects are following the strict Newtonian laws, there is a kind of almost spooky way in which they begin to seem to act in a kind of teleological manner as a group. And it's possible to solve problems in physics using the Lagrangian and the Hamiltonian that would be intractable if you tried to perform individual calculations on all the particles in the system. And that's even on a classical level. Similar things apply in the quantum realm. And Richard Feynman, for one, devotes a whole sort of anomalous freestanding chapter in the Feynman Lectures on Physics to the problem of action, of least action, and how it is that a system manages to transform itself from one time step to the next in a manner that minimizes a quantity called the action. That's all pretty hand-wavy, but it's a way of saying that pre-established harmony, although it sounds ridiculous, is might have some exemplars in later science. And finally, I'm just going to talk a bit about Gödel's work. Gödel was a very strong mathematical Platonist, meaning that he believed that the subject matter of mathematics was real, not just made up by humans, and that it existed before humans came along and invented it. So it's actually a point of view that would be uncontroversial now in a lot of math departments, a lot of physics departments. But where he came from, which was Vienna in the first half of the 20th century, it was controversial, and he apparently felt like it was a proposition that needed defending. He devoted a large part of the last half of his life to finding ways to defend it. He felt that monadology and Leibniz's thought in general solved a lot of important problems that needed solving. He was aware that Kant had raised very serious objections to it. He took those objections seriously, and he devoted a lot of effort to trying to counter those objections. So, in one of the weirdest facts I've ever seen from history of science, Gödel became sufficiently conversant with general relativity that he was able to come up with a set of solutions for Einstein's equation that apply in a rotating universe, proving that in a rotating universe you can achieve time travel. Since we're not in a rotating universe, it's just a sort of curiosity, but and many people would have seen that as a nice little paper and nothing more than that. It's remarkable that a man who was a logician was able to write such a paper, but the fact that he went for walks every day around Princeton with Einstein probably helped. Anyway, it appears that his ulterior motive for doing this was that he felt that if he could call into question the reality of time, it would enable him to kick one of the props out from under one of Kant's objections to Leibniz. Later in his life, he decided that Husserl, Edmund Husserl, the phenomenologist, had kind of solved this problem, that he had figured out a way to reconcile Leibniz's work with modern thought, and he undertook an obsessive study of the works of Husserl, which is the only thing I've ever seen that's more difficult to read than Leibniz and Gödel himself. So I don't recommend it as light recreation, but in his mind, this was the answer to some serious problems, and he developed a theory. Gödel was clinically paranoid, and he developed a theory that Leibniz had actually achieved the creation of the Characteristica Universalis, and that it had been hushed up by a conspiracy of scholars. What's probably the case is that nobody knows, because people, even today, are still sifting through all of Leibniz's papers, and so it's difficult to know what Leibniz did and did not actually accomplish in that vein. I'm just going to read sort of the conclusion of the piece that I wrote on this a couple of years ago, and then open it up for questions. Leibniz's most fundamental assumption, namely that the universe makes sense and that the human has the power to make sense of it, and that consequently pure metaphysics is no waste of time, remains perhaps the central question of all science. In 1960, Eugene Wigner wrote a paper, The Unreasonable Effectiveness of Mathematics in the Physical Sciences, in which he addressed the nearly miraculous way in which pure mathematics, seemingly a product of human cognition and nothing else, predicts the behavior of the physical world. The examples cited by Wigner would have made sense to Leibniz. Leibniz, however, would have been baffled by Wigner's use of the adjective unreasonable in the title of his paper. Wigner was a modern, a product of a skeptical age. He was uneasy, or felt obliged to pretend to be uneasy, with the philosophical implications of the way in which the physical world answered to mathematics. This unease could not have been more alien to Leibniz, who, during his long philosophical career, questioned many things that would have been easier to leave alone, but believed with a kind of medieval serenity in the reasonableness of creation.